This is part 3 of chapter 14, electrode potentials. So in part 3 we're going to talk through relating our potential, our voltage values that were discussed in the first two videos to equilibrium, and discuss reference electrodes. So galvanic cells, that's the redox reactions where we have half of it's happening in one beaker, half of it's happening in the other beaker. There's a salt bridge between them. There are electrodes, and then wires connecting the cathode beaker to the anode beaker, the plus to the minus beaker, and then there's a potentiometer that measures the voltage in between. So galvanic cells, because electrons are moving from the anode to the cathode, electrons are moving along a wire. We've made a current, we've made electricity. So galvanic cells make electricity, as long as we're not at equilibrium. Once it gets to equilibrium, the overall cell potential goes to 0, which means electrons are not moving, and so galvanic cells, like batteries, are just galvanic cells. So if you think just about your AA batteries that you use, when your battery dies, what happens is that your anode and your cathode are now at equilibrium. You've got a cell potential of 0. It's not doing you any good anymore. Okay, so we do have a relationship between cell potential and equilibrium. Okay. So this was mentioned earlier, but if you see a potential with a degree sign, that's just telling you standard conditions. So what the potential would be under standard conditions. All reactants and products that are aqueous would be 1 molar or 1 activity, and all reactants or products that are gases would have a pressure of 1 bar. And to figure out the cell potential under standard conditions, we would not need to use the Nernst equation. The Nernst equation, which was video 2, talks through how to figure out the cell potential if you're not under standard conditions. If you are under standard conditions, all we need are the standard potentials that we would look up from the appendix C. We could look up a half reaction, see what its standard number is, take the cathode minus the anode, and we would get the overall standard potential. Okay, so let's just do one example of that. So if this is the reaction that's happening, in one beaker, I have silver chloride and silver, and so silver chloride solid, and then and silver metal and chloride ion. And the other one I've got iron +2 and iron +3. So these are my two half reactions that are happening. I've got them in 2 separate beakers. I've got wires between them. I've got the salt bridge. It's all great. So I want to figure out what the potential would be under standard conditions. Okay, so this is under standard conditions. The molarities are 1. There are no gases, but if there were, their pressures would be 1 bar. Okay. So using the equation from that last slide to figure out the overall standard potential, I just need to take the standard potential of the cathode minus the standard potential of the anode. So the way I'm going to figure out which one's the cathode and which one's the anode, of the two standard potentials, the one that's the most positive number is E+. The one that's the most negative number is E-. This is true as long as we're using galvanic cells, because the definition of a galvanic cell is that it's a spontaneous reaction. So in that case, the cathode will always be the most positive potential. That's the direction the electrons will always move. So the standard overall cell potential would be whatever I get for 0.771 volts minus 0.222 volts. So I get 0.549 volts. So if we're looking at standard conditions only, we can get the overall cell potential without the Nernst equation. Just take the positive minus the negative. If these molarities were given and they were anything other than 1, we would have to do the Nernst equation to figure that out. Okay. So I mentioned that equilibrium and cell potential are related. So capital K is just remember the equilibrium constant. So using the Nernst equation, I'm not going to go through where exactly this comes from. You're just going to have to believe me. But using the Nernst equation, here's the relationship between the standard cell potential and the equilibrium constant. So lowercase n still stands for the number of moles of electrons. So I mentioned that when something is at equilibrium, its cell potential is 0. So when it's at equilibrium, E is 0. True. But in this equation, what we're looking at, the E degree sign, is not its potential at equilibrium. E degree sign is its standard cell potential. So this number we would figure out like we just did on that last example. We would look up the two half reactions from the appendix, take the E plus minus the E minus, just from the back of the book. That's where our E degree sign would come from. So this is the relationship between the cell potential and the equilibrium constant. So let's do an example calculation. I'm just going to take the same example we had earlier. So what we got, you can backtrack if you need to, was 0.549 when we took the E plus 0.771 minus the E minus 0.222. So if I'm going to do the calculation to solve for equilibrium constant, I'm just going to rewrite the equation from the last slide. 0.05916 over n base 10 log of k. So I can plug in E degree sign and I can plug in n. So E degree sign is going to be 0.549 volts, 0.05916, and I haven't been doing this, but technically this unit of that number is in volts. That's how the units cancel. N is 1. We're looking at the coefficient of the number of electrons. And then log of k. So I'm trying to solve for k. So I would divide both sides by 0.05916, and I would end up with 9.2799 is equal to the log of k. So I would do 10 to the power of both sides. So 10 to the power of 9.2799, what I get 1.9 times 10 to the 9th as an equilibrium constant. And as long as our cell potential, our standard cell potential, is a positive number, we would expect this to be a giant equilibrium constant. This is, almost 2 billion. So this is a big number. That's not surprising because galvanic reactions are spontaneous. That means they make a lot of products. They go towards the products. Okay. So we could solve for the equilibrium constant if we needed to, based on the cell potential. So related to this, I talked about galvanic cells are spontaneous. So this is just relating the cell potential to the Gibbs free energy. So the Gibbs free energy delta G is what definitively tells us if a reaction is spontaneous or non-spontaneous. So I have the same equation on here twice. The first does not have degree signs, the second one does. This means this equation works for both standard conditions and non-standard conditions. So the same as it's been this whole chapter, lowercase n stands for the number of electrons, F is the Faraday constant, and the E is the cell potential. So the overall cell potential. So you could just multiply these numbers, convert the cell potential to Gibbs free energy. I did not do an example on this one. So looking at reference electrodes, so we've got our two beakers. Think galvanic cell, you've got your two beakers. The indicator electrode is the beaker, or the setup, that we're trying to measure. It's the one we're interested in. So we always make sure that E plus is our indicator electrode in a galvanic cell. So if you're trying to measure the potential of iron plus 3 to iron plus 2, that would be your indicator electrode. The reference electrode is the other beaker, the other container that's connected to the indicator electrode with the salt bridge. So we got our two beakers, the cathode and the anode. The cathode we would deliberately set up as our indicator electrode. Our anode would deliberately be set up as our reference electrode. And that reference electrode, we already know its potential. So E minus, if we're using a reference electrode, E minus would be a known value. So we can get the overall cell potential from the potentiometer, the voltmeter that's there. And if I know E minus, I can solve for E plus. Okay. So the E is looking at the indicator electrode. So it's like we're trying to solve for the indicator electrode. So again, just a reminder how this worked. Where's my pen? There we go. Okay, so solving for the cell voltage, we took E plus minus E minus. So again, if you know E minus because it's a reference electrode and you already know what it is, and you get E, your cell potential, from your data, then we're solving for E plus. So with our reference electrodes, to make things easier, if it's a reference electrode, we know what its value is and it's consistent. So they've made these smaller and you don't have to set them up as an entire beaker every time. So in this image, the reference electrode looks here like a pH meter. That's this. They just made it small. So this is the reaction that's happening in there. It's the silver solid, silver chloride solid, and chloride hanging out in there. So that would be the reference electrode. The indicator electrode is this iron reaction that's happening. That's the one we're interested in. This platinum wire coming out, the reason why that is there, usually it would be like iron metal, whatever the metal is. Well, the half reaction we're looking at is moving iron between +2 and +3 charge. Neither of those are a solid, so we couldn't have a chunk of either of those sticking out. Platinum is just the thing that's being used to conduct the electrons. Platinum is not changing, it's not being reduced or oxidized, it's just the thing that the electrons can move between. So it says that the platinum wire is the indicator electrode. It's officially the electrode because that's what's conducting the electrons, but the half reaction we care about is this. This is what we're trying to solve for. So we would get the E from the voltmeter, we would know the potential here. But these reference electrodes just make things smaller, neater, and easier. You buy them. You could make them, but I would buy them. So I'm just going to give you the most common reference electrodes. So the silver chloride, which is the one that was used in the last image. And these things look kind of like pH meters. The silver chloride has silver metal, silver chloride solid, and chloride element in there. Its standard reduction potential is 0.222 volts. So if we looked it up in the back of the book, that's what it would be. But if we take into consideration the chloride, so think like activity. If we take into account activity because of the chloride, the potential is 0.197 volts. So unless I tell you otherwise, if the question mentions a silver chloride reference electrode, the potential you're going to use is the 0.197 volts. You do not need to memorize that. I will give you that, but that number comes up a lot. Because a lot of times, if we're just interested in one half reaction, why go ahead and set up a whole nother beaker? Why not just use a reference electrode that you've already purchased? Okay. So silver chloride reference electrode is one of the most common. The standard hydrogen electrode was mentioned in, I think, the very first video with this chapter. The reason why, and that one in a lot of ways is the best because its potential is 0. So it makes it very easy to figure out the other potential. But the reason why that's not the one that is most commonly used, even though it makes the math the easiest, is you have to use a gas, and it's challenging because it's not just that there has to be a gas inside of the electrode, but you're creating a gas in there, and we don't want the pressure has to stay 1 bar, so it's just an added headache. So the silver chloride is one very standard one, and again, 0.197 volts is its potential. These reference electrodes, if they're mentioned in the question, they will be the E- number. So another common one is the standard Calomel electrode. So sometimes you see S.C.E as its abbreviation. So we looked it up in the back of in the appendix. Its potential would be 0.268 volts. But if we take into consideration if it's saturated in potassium chloride, which means there's a decent amount of chloride, taking into account activity, its cell potential is 0.241 volts. So unless I tell you otherwise, if the question mentions a Calomel electrode, I want you to use 0.241 volts as the number. So in this we've got mercury. So the last one was silver, this one is mercury. In both cases they're not the cheapest things. We definitely don't want to break our Calomel electrode if we don't have to. So this is just a scale that the textbook gave us on 8 ways to convert back and forth. Because if you're using these reference electrodes, you're not going to get the number that you would predict from the table in the back of the book. The table, that appendix, those standard reduction potentials that we've been using in our Nernst equations, those were obtained by using the standard hydrogen electrode, which I'm pretty much telling you we're not going to do at all. We'll be using either the Calomel or the silver chloride. So we need to be able to convert back and forth between them. So the textbook uses this kind of number scale thing, and that's glorious. I'm going to do some examples. I'll show you kind of how I think through it, and then you can decide what works for you. But it's just, so the 0.197, that's the silver chloride. The S.C.E is the Calomel, the 0.241. Those are the 2 numbers that we're going to be using. So it's just the number that you get from the back of the book or from the Nernst equation is going to be the number that you have obtained comparing it to the hydrogen electrode. Then you need to convert it. So anyway, like I said, we're going to do some examples. So 2 example questions. If I want to figure out what the cell voltage, so the E, not the plus or the minus, but the E, if I've got the iron 3, iron 2 half reaction with a reference electrode that is the saturated calomel electrode. So what I have here given to you was what the iron 3, iron 2 half reaction is. So this is coming from the back of the book. So again, this is coming from the back of the book. That number is assuming we're using the standard hydrogen electrode. Well, I'm telling you we're not. We're using the calomel electrode. So let's figure out what we would get. So the equation that we're using is still just the cell potential is E plus minus E minus. The reference electrode is going to be E minus. So E minus is going to be the potential for the calomel electrode. E plus is going to be the potential for the half reaction that we're looking at, which is here. And then E is what we would get from our potentiometer, our voltmeter. So I'm going to plug 0.771 volts in for E plus, and then E minus is the calomel electrode. That's the one that was the 0.241 volts. So if this was my E plus, the iron, and my E minus was the calomel electrode, what my potentiometer would tell me is 0.530 volts. So even using a reference electrode, I wouldn't see 0.771 on the instrument, I would see 0.530. All we're doing is using the same calculation we've been using. You just need to plug in the number for the reference electrode as E minus. So that one was just, okay, what would I get if I use these two? The second one, we're going to convert an E, so the cell potential value that was used for a silver-silver chloride, like when they did it, they used a silver-silver chloride reference electrode, and I want us to figure out what the electrode would have been if we had used a standard hydrogen electrode. So this is where they use the number line thing, and this is what I do. I still just fall back to this. E is E plus minus E minus. E minus is going to be the reference electrode. So in this example, so negative 0.111 volts was the potential they got when they used the silver-silver chloride reference electrode. Okay. They don't tell us in this question what E plus is, what its value is, what the element is, nothing. But negative 0.111 volts, that's what they got, that's this number. So let's just go ahead and plug 0.111 volts in for E. I do not know the cell potential of the indicator electrode. It says that the reference electrode was silver-silver chloride. So the potential for silver-silver chloride that I told you to use is 0.197 volts. So if I just plug those two numbers in, can do a little bit of math and get 0.086 as my cell potential for E plus. That's just beautiful. Okay, so negative 0.111 is what the potentiometer says. This is the actual potential for just that one half reaction. So the question then says, what would the potential have been with a standard hydrogen electrode? Well, in this case, we're solving for E. We don't know what the instrument would have said. E plus, we just solved for that, 0.086 volts. E minus is the reference electrode. So the standard hydrogen electrode, if you go back and look, it's 0. So the instrument would have given me 0.086 volts. So I don't use the numbering line, I just kind of use this equation to solve for this. Again, you don't have to memorize the calomel and the silver-silver chloride reference electrode potentials, the 0.241, the 0.197. I will give you those, but they're going to be used a lot, so have them handy, especially when you're working on sapling.